For today's lecture, we are going to review what we have done yesterday, and then we are going to do an exercise. Now, watch me showing an example, and you do the homework at home. So this is the problem that we have seen multiple times, so I don't need to explain too more. However, different from what happened in the past is the red line, red sentence. This time, the shaft is not rotating. Okay, this one is not rotating. But the belt tension loads fluctuate between the following two conditions. So it's like maybe there is a machine connecting, having the belt connecting to the shaft, and it's operating some kind of periodic motion, and it dynamically tighten the belt and then loosen the belt a little bit. So maybe there is a periodic motion that is constantly changing the tensile force within the belt. That could be happening if you have some kind of mechanism that is not doing exactly the same thing for the entire cycle. Okay, so if that happens, then the tension applied to the belt will be having higher stress for some moment and then lower stress in other moments. So it's like if you look at the stress, probably it's like a sine wave. Or maybe the entire system is something in your car, and your car is driving on a bumpy road. So the entire car system is constantly having some motion. So if that is having some motion, the belt tension could be varying with time. So when the problem said it's fluctuating between two conditions, it's just like the loads are having a situation like this. This is time, and this is the tension. Okay? And because of the tension is fluctuating, so when we compute for the shear diagram, moment diagram, there will be two extreme conditions, the one at the very top and the one at the bottom. So we will treat, so this is like two extreme conditions. Condition, let's say this is number one, this is number two. So it's like we need to compute the whole thing twice. One is the upper extreme, the other one is like the lower extreme. Okay? And of course, this doesn't apply to everywhere, because when some loads is greater somewhere, maybe at some other positions it's lower. So you never know. You need to truly do some calculation to figure out. So what I did was exactly what we have done, but this time I derive everything with math symbols. I have not yet applied the numbers in, because later on, when we try to study two extreme conditions, I can easily apply numbers to those math symbols. So this is what we have done already, but in this demonstration, I didn't plug in the numbers at the beginning. I derived with math symbols. Okay, so you should be familiar with this already. And Now I plug in the numbers. So for the, let me see. After I plug in W1, W2, W3, and W4, I can solve for all the values. So the reaction forces can be determined by the W's in two conditions. And then once I have the reaction forces, I can also plug in into the equations for shear, and I can plug into the equation for moment. I can even know where is the largest moment. Once I have those, I already compute everything. And then from the shear diagram, shear equations in the previous page, and the moment equation in the previous page, if you plug them out, it looks like this. So it's like for the shear in the entire shaft, the shear force is fluctuating within the two boundaries. So as time goes by, the shear at this position is like this. Okay, and the shear right here doesn't change too much. For the moment, it looks like this. So for mechanical design, we care about the worst loading position, the position with the largest stress. So I plug in the equation for finding the maximum moment. Of course, because the value of W3 and W4 is not the same in both conditions, and of course the constant won't be the same. However, if you observe from the diagram, from the figure, you realize they are actually not the same position. It's slightly located at a different position, but it's very close. So around this area in the shaft, it's always carrying the largest bending moment. Slightly shift left and right in two conditions. So it's like, if I make the drawing of the shaft, let's say this is a shaft. Maybe the moment max is right here in condition number 1. And maybe in condition number 2, it moves a little bit on the side. So it's like in the very close area based on my calculation. Okay, so this area is quite bad. Let's just assume they are at the same position and try to see how this worst position is having bending moment constantly changing with time. So we would like to compute its average value and the amplitude. So at that position, the mean value of the bending moment basically sum them up divided by 2, and the amplitude basically is half of this gap, right? Here's the mean value, here's the amplitude, based on what we introduced yesterday. So that's why for the amplitude, we use the larger one minus the small one divided by 2. And over here, although here is negative, but I'm showing the amount with an absolute value, absolute sign. So this is the position with the greatest bending moment. Okay, and for the torque, because how the belt tension is changing with time, so the torque is changing with time as well. So it's like the fluctuating belt tension is twisting the shaft like this. Okay, sometimes tighten, more tighten, sometimes a little bit loose. So it's like doing something like this. So you also need to figure out the mean value of the torque and the amplitude. But when I create this PowerPoint, I made a mistake. I didn't modify it. So if you look at how I computed the torque, this is what is 5. 5 is basically the difference between the two W's. So if you see in condition number 1, the difference between W1 and W2 is 5. Okay? So it's like a delta W is 5. So if you use a delta W times the distance right here, that will be the force, the delta force. And if you use the delta force, delta F, times the radius, that will be the torque. So in condition 1, you will use the difference between them times because it's a distributed load, you need to multiply the distance to get the total force at the edge. And multiplying the radius, you have moment. At the time, I was multiplying the radius, and the radius was 40, right? So this is the difference of W's. This is the distance right here. This is basically the radius. And from here, you can see I directly use it to represent the torque inside the shaft. However, if you truly take a look at the problem, if here is the force, then the force that is at the boundary of the shaft will be smaller. So I didn't. So if this is the amount of your torque, let's say this is the amount of your torque, like the value I computed, then I should use this smaller one, because if I assume the torque is linearly distributed inside the shaft and the pulley itself, then the torque should be slightly smaller. But in my slide, I didn't do it. So that's the mistake I made in the past. I didn't modify it. To be precise, you need to make it a smaller one based on the diameter, and then the ratio between the diameter and the outer diameter. So anyway, just for you to know, that part is wrong. But compared to the moment, torque is quite small. If we multiply this, the torque will be even smaller. So I think in the exam 1, I even mentioned, please ignore the torque, because in all the problems I made in this kind of diagram, the torque I designed in the problem was very small compared to bending moment. So that's why in the exam 1, I said just ignore torque. Okay, so if you can do this, you realize the shaft is actually not rotating. However, due to fluctuating bending belt tension, the moment inside the shaft and the torque inside the shaft could be varying with time. So if you now work on the Mohr circle and try to evaluate the principal stresses, you realize the Mohr circle will be changing its shape with time. So when I draw this red arrow, it's actually representing the Moore circle in two different conditions. So in one condition, the Moore circle is like a smaller one on the left, and in the other condition is a larger Moore circle on the right. So if you try to compute the principal stress, there would be a mean value and amplitude of the principal stress, because as time goes by, the Moore circle is changing its shape, smaller, bigger, smaller, bigger. So there, the first principal stress could have a mean value and an amplitude. So I did the whole thing, and then I figured out this is the first principal stress and the second principal stress. This is the first one, the mean value, second is the amplitude. So you do all that. Once you complete with that, you realize, okay, the principal stress 1 is having a mean value of 81 megapascal plus and minus 21. Similarly, for the principal stress number 2, mean value is negative 0.13 megapascal plus and minus 0.08 megapascal. So this is small, okay? If you can do that, then we can now talk about fatigue. So before we talk about fatigue, we can apply everything that we talk about in the von Mises stress. The equation for this 2D problem is given like this. The equation of von Mises stress is given like this. And you can treat the mean part and the amplitude part separately. Just plug in the numbers. So overall, equivalently, the most loading area, the worst loading area, is having a mean value of von Mises stress in 81 megapascal, plus or minus the amplitude, 21 megapascal. Okay, so that's the directionless loading condition, because von Mises stress is a stress value that doesn't have direction. It's not any stress along any direction. It's a stress level. It represents stresses everywhere. Once you have that, now we have the fatigue model. We can apply to fatigue model with the information of the material property, including yielding strength, ultimate tensile strength, and also endurance limit. I already give you some numbers. As an example, I apply to the yield line, Goodman, and Soderberg models. Only differences are at the bottom. For the yield line at the bottom, they are both yielding strength. For Goodman, I didn't use the modified one, I used the original one. So original one is a second line that is more conservative on the amplitude, but more aggressive on the mean value. So the extreme of the mean value is ultimate tensile strength. The extreme for amplitude is endurance limit, a lower value. Soderberg, which is the most conservative model, conservative both on the mean value part and the amplitude part. Now, plug in all the numbers here. You will get different values of n, basically the safety level. And you need, once you see those, you need to be able to study what those safety level means. So for the exactly same condition, same loading condition, same material, the only difference is that we have 3 different math models from different concepts with different levels of conservativeness. So we should end up with safety value, safety factor value in different levels. So if we are very conservative, the design should tell us, right now you are having a lower safety level. So from here you can see the most conservative Soderbergh model telling us your design now is having the lowest safety level. So this is how a conservative model will give you. It tends to give you a lower safety level to remind you maybe you should be more safe, to be safer. Okay? And what's the most conservative, most aggressive model? Soderbergh. Because it even has a line that is crossing the yielding line. So it's having the highest safety level. So the model tends to tell you, oh, you are quite safe. So you can do more. You can carry more loads. You can make the structure weaker. You don't need to be this strong. So aggressive model tend to show you higher safety factor level. Okay, so sometimes people are confused. Oh, when I use this model, I have a high safety level. Good, that means I'm safe. But that doesn't really is not really the what the model is about. The model is actually the most aggressive one. So it tends to give you results of higher safety level to let you know you are safe. But this result comes from how aggressive the model was. Okay, so the yield line is at the middle. So it really depends on how aggressive or how conservative you are in the future when you are a designer. Then you will choose your own model. The three models are not the only models in the research field. Let me show you some other models. Okay, like this. So this is exactly what I told you from yesterday. Sorry. The dash line is the yield line, right? From yield strength to yield strength. The dark line, straight line, is the Goodman. Sometimes people even call it modified, but it's the Goodman. The combination of these two often is called modified Goodman. But anyway, people tend to use different names in different areas, but the concept-wise is the same. Goodman is more conservative for amplitude, but more aggressive on the main part. And these are the two models. If you try to read more, you can actually see this, but it's a diagram I try not to use because I feel like this one is more confusing. I like this diagram more. But if in the future you read more, you realize, hey, how come in the class Professor Lin didn't mention this? Basically, this is a diagram including mean part and the dynamic part at the same time. So I don't like this diagram. So I didn't mention that. I didn't mention it too much. Okay, like this one, this is more like the modified one. Having a Goodman boundary here and a yield line boundary here. But what I really want to show you is not showing. So maybe how about this one? From here, okay, from here you can see many more different models. Let's first look at the ones that we are familiar with. Okay, so those ones share the idea of Goodman. The amplitude part cannot be larger than endurance limit. So they all follow this idea. But for the mean part, every model has a different concept. So if we look at the green one, it's the Goodman. The blue plus one, are they plus or cross? A lot of plus, and a lot of, I don't know how to describe it. So this particular blue one on the left is the most conservative one, Soderberg. So there are other researchers believe design shouldn't be linear. Just like how we introduced the failure model 2 or 3 weeks ago. In the beginning, we have a maximum shear stress model where we have linear boundaries. But we really didn't mention, for the linear boundaries, let me remind you of what I'm talking about. For the failure, we had linear boundaries like this. This is the maximum shear stress model, right? So this model came from very simple ideas. So design boundaries are straight lines. But in fact, in reality, people have done research, maybe have done a lot of experiments and realized, hey, those are linear boundaries may not be true. They realized there's still some space at those linear edges. So they started to derive design models from different concepts, such as the distortion energy model, the strain energy model. If you view the same problem in a different aspect, sometimes you derive new equations. That's why at the end, people found the maximum distortion energy model, which is having rounder edges that allows you to have some space, extra space for your design. So I think for fatigue, that's a similar situation. When the first couple researchers developed design equations for fatigue, they start with linear models. It's simple. You don't really need to just derive with complex equations. And I believe there must have been researchers done some experience and realized, hey, at the middle, your estimation of this safe limit is not quite accurate. So people started to form different mathematical models. So let's take a look at this red one. Red one is the elliptical model. So people try to use the same corner points, but different shapes, starting to use nonlinear shapes. So here, the red one is an ellipse. And the ASME, the American Society of Mechanical Engineers, they define this elliptical shape, but using the yielding strength as the upper limit for the mean part. And there's a different model called Gerber. Gerber used basically also a curve, but not elliptical. It's a different method. I don't remember what equation, but basically another curve. Gerber is more aggressive, which is using ultimate tensile strength as the upper limit. And there's an elliptical model in the light blue shape, which is very similar to the ASME elliptical model, but more aggressive on the mean part. And the most aggressive one, I would say, is this one, Marrow. It's having, I don't remember what is sigma F. Maybe the stress for failure, maybe. I'm not really short. I need to read the description. But anyway, I just want to show you that the three models that I introduced to you are the most fundamental models. They are different models from the literature. So this textbook and also this lecture cannot tell you everything. If in the future you're interested and you realize, hey, the model that the Professor Lin told me probably is not accurate enough, maybe some other solutions can be found from the literature. Okay? So let's get back to our slide. So that's the first example. I have a second example. Exactly same problem. But here's the thing. Now the shaft is rotating. Still the same fluctuating bending, the belt tension, but this time the shaft is rotating. What's gonna happen? So let's say this is a shaft, and I already have fluctuating belt force, but I'm also rotating. That means sometimes somewhere at the top of the shaft could be carrying compression, could be compressed, but when it rotates to the bottom, it's being pulled, being tense, having a tensile condition. So the fluctuating stress condition in the shaft will not be the same as the stationary shaft. If the shaft is rotating, you need to think about how this low condition is going to look like inside the shaft. So this is what I found. Remember from the first problem, when we talk about the moment, there are two extreme cases. They're both negative. If negative represent compression, that means somewhere inside the shaft, if it's rotating to the opposite side by 180 degrees, the stress is gonna become tensile. So the low condition could be something like this. So when it's being compressed, it's fluctuating, and when it's being pulled by tensile stress, it's also fluctuating. So the curve right here are just some schematic, but it's showing how the entire low condition could be happening. So in this case, what do? You just treat the somewhere inside the shaft is having a mean stress at zero, because you can directly say, okay, it's having a zero mean, but this large of amplitude, because that's the worst condition that could be having as the stress fluctuates. Okay, that's why we can consider something like this. Okay, so then, do you think it's will you be worried about whether this is an accurate estimation? Because maybe the stress profile doesn't look like this. Maybe the mean value is not exactly zero. Maybe if you truly have a system like this, and depends on the frequency of the belt fluctuation, and also the frequency of the rotation of the belt, maybe averagely is not at the mean, maybe slightly off. And also the amplitude is not exactly at this. You're right. In reality, this may not be right. But mathematically on paper, you can do this kind of estimation. So I would say when we are solving problems like this, you can have your idea of describing how this stress look like. Maybe you have a different viewpoint, but you have to have good reasons. And definitely whatever we're doing on paper are just estimations. So if you agree with the load condition that I'm talking about right here, then we consider that loading condition as zero mean and the amplitude level of 271.724. Okay. For the portion, you realize I didn't change anything. Why is that? Because even though we are twisting the shaft fluctuatingly, sometimes tighten, sometimes loosen, we are twisting the shaft entirely the same everywhere at any position. So even when the shaft change its angle to a different place, we still twist the whole thing the same way. So I believe for the fluctuating, for the twisting condition, it doesn't matter if the shaft is rotating. So that's what I believe. That's why the analysis for torque is exactly the same. Okay? So if you believe in that, then what would be different would be how you plug in the numbers. So because the shaft is rotating, based on my calculation, I realized the first principal stress is having a mean value of 3.2, but the amplitude is 100. So the mean value of S1 is right here, plus or minus 100. Okay? And the principal stress number 2 is the same, and with a small amplitude. So principal stress number 1 sometimes even become principal stress number 2 when it goes to the negative side. Okay? So the Mohr circle is changing its sides, sometimes mostly in the positive side, many times on the negative side, based on my calculation. So even the shaft is carrying this unique condition, you still can do math. So just plug in the whole thing. Overall, use von Mises stress, and we realize the mean of the von Mises stress is 5.54, amplitude is large. So equivalently, the worst loading condition is carrying a mean von Mises stress of 5.54 megapascal, plus or minus 103 megapascal. So it's averagely it's not very large, but amplitude changes dramatically, plus and minus, plus and minus. So somewhere inside the shaft is being compressed and tensile, compressed, tensile dramatically. So if you apply this in your fatigue model, you realize all the safety factors reduced. Earlier recall the problem without rotating. What happened was, in the first example, if the shaft was not rotating, the amplitude part was not that dramatic. But in this situation, when the shaft is rotating, the stress level inside the shaft constantly changes from tensile to compression and then back and forth. So from our common sense, we know if you bend something both ways constantly, then you should be generating fatigue issues. And the fatigue model tells us the same thing. Still, the Soderberg model is the most conservative one. But this time, Goodman is giving us lower value than yielding. Why is that? Because when the Goodman model looks like this, and this is the yielding, this is a yield line, and this is Goodman, right? So Goodman is more aggressive on the average part, but it's more conservative on the amplitude part. So if a material is carrying more amplitude part of stress, Goodman is actually more conservative. So from here, just like what we have found, in this second example, we have stronger amplitude part. So our design point is somewhere closer to the vertical axis. And our design point is having more serious issues on the amplitude part. That's why Goodman is showing a lower value of safety in this particular problem. Okay? So when the shaft is not rotating, they are all safer, all models are safer. But when the shaft is rotating in this particular problem, all models are giving us lower safety because of this fluctuating stress. Just like what happened in the previous problem, Soderbergh is the most conservative one, but this time Goodman is the second conservative one. Yielding line is the least conservative one. Okay, so do I have more slides? No. Let me see if I have. This is this one, right? Let me see. What do I have here? Oh, this is what I have already. Okay, let me see what's next. Stress concentration. So basically the same problem, but now consider stress concentration. Okay, so I don't think I have enough time to go through, so I'm going to just quickly talk about it. And I will give you a homework. Exact same problem, not rotating, exactly same example one, but now if we talk about stress concentration, something's gonna happen. I am not going through details today, but I'm just telling you, if we need to consider stress concentration, this is where we need to do some analysis. And then we need to plug in. Oh, where did I plug in? Here. If you take a look at the principal stresses, I am applying some multiplier in front of all the stresses. They are the K times larger of the stress at the position with stress concentration. And this is how I like to remind myself what are the K values for different stresses. Static, normal, static shear, dynamic, normal, dynamic shear. So if I write it down next to me, when I solve the problem, I can easily grab the right K value. So I won't make mistakes. So here, I compare with the earlier slide. These are the values without stress concentration, and these are the values with stress concentration. It seems like it seems like with stress concentration, we have greater stress levels. Earlier, the mean value was 81 plus and minus 21. But now, with stress concentration, the mean becomes 143 plus or minus 33. So much worse. Okay, so but in this case, I did something so we need to talk about stress concentration in this particular problem, but I'm not focusing on that part today. I'm just letting you know if we need to apply stress concentration factors, this is how I handle those. The rest are the same. Okay? So I think I will shift this PowerPoint to the next lecture. And in today, I can give you an assignment. I think I will ask you to solve the same problem, but with some modifications, so you have to try it by yourself. Let's try the, not this one. Okay, I think this figure is fine. Let me turn into full screen. And let me move up. I think if I make the torque matters more, I will change the value here. If I add everything by 20, then everything will torque matters more. So if I do this 25, 30, so everything plus 20. So that should be solvable. So this plus 20. But if I want to fluctuate more, I think that's fine. Plus 20, plus 20, 28. So here, 55, 43. Yeah. So, solve for what? Solve for reaction forces, shear, moment, worst moment, position, and then more circle. Once you have more circle, then principal stresses and volumetric stress. Once you have that, you can do 3 fatigue models for safety factors. That's what we have done. But do this for do all this for number 1, shift non-rotating. Number 2, shift rotating. So basically, you will do exactly what I have done. You can use some of my slides, But over here, you will face an issue. Do you compute the torque of this one? I think so. Yeah. So please, when you compute the torque outside, you need to just assume torque is linearly distributed in shaft and pulley. So you will use this one. Use this torque for shaft design. Yeah? Do I need to mention anything else? Yeah. So this is your homework. I don't think you need this. And you don't need this. Okay. And if something that if you need to make proper assumption, please do proper assumption. For example, the worst moment position is changing, right? Sometimes left and right. Just assume they're the same point. So do proper assumptions so you can solve the problem more easily. Okay, it's just a homework. So I'm not too serious about how you solve it. But I think I want you to gain the experience of solving everything when something is fluctuating, when the shaft is rotating, and experience what's going to happen. My slides provide some information you can follow. I know the whole thing takes a long time to finish, so you might need to be patient about the procedure. Okay, you can solve by hand. You can write it down in iPad and print out, or figure out a way to solve it. Yeah.
How about the yield strength or automatic strength?
Same condition. Thank you. So in this particular slide, there are some material properties. So use the same material property. Okay, thank you. Okay, so that's homework. You have your double 10 holiday to work on. See you.